In this example, we're now going to look at why roads are embanked to provide additional safety for cars going around them under different road conditions. Like when you travel on the off-ramp on the highway, typically they're embanked at least a little bit. So that's what I'm trying to show here. If you're looking at the car coming at you, you have this kind of curved road, and the car is coming at you around the bend this way. So the road is embanked by an angle theta here from the horizontal. Okay. Gravity is in the problem, so we're going to put gravity straight down. And even though this diagram looks like the box sliding on the incline and we rotated our coordinate system, when you're looking at circular motion, where a car or an object is on an embankment like this but traveling in a circle as shown here, we do not rotate our coordinate system. So please put that in big bold letters on this page of notes so you will know you do not rotate your coordinate system for these types of problems. So the first thing we are going to do is put in our dashed, not rotated, coordinate system. We can leave mg straight down, and radially inward is our positive direction for circular motion. So the center of the road is going to be somewhere over here. The radius of curvature that it's following, little r, is following that center dashed line where the car is actually going in the circle. And that is our coordinate system. That is really important. You will not solve this problem correctly if you rotate your coordinate system and look at it like a box on an incline. So leave the normal y-axis up and down. Radially inward axis is our positive direction, and it is not rotated. So let's first think about what will happen if there's no friction in the problem whatsoever. So as we said, when we have boxes on boxes with friction, we first eliminate friction and then include friction after we understand what would happen without friction. Well, without friction, the only force that we have other than gravity would be the force normal. So this force here, right, the force normal. And let's take a look at our angles. So take a moment and convince yourself that the angle theta down here and the angle theta between the y-axis and the force normal is actually the same angle theta. So we have a lot of like 90 degrees going on here, so I don't want to put it in, but if this is my angle theta down here, this is also theta, so that orange theta and this angle here make 90 degrees, so that's why that orange theta also is theta. They're the same theta. So that you don't want to go through a lot of geometry pain with when you solve these types of problems. You want to automatically know that the angle of the incline will be the angle theta that the force normal makes with the positive y-axis. So then we can set up our equations, and again, friction we're not putting into the problem yet. So just the embankment, and that will show us what the embankment is doing for us. So in the what I call the ideal case or the design case for this road, we're not including friction. So the only y direction forces we have are going to be the force normal cosine theta, which is this vector here, and the force normal sine theta, which I'm going to draw down here in the radially inward direction. So those are the component vectors of the force normal, and that is what I'm going to use in my analysis for Newton's second law. Well, now we're in business. Force normal cosine theta minus mg equals 0, so I have an expression for force normal. In the radial direction, I do have a radial force. The normal force is providing a radially inward force, the sine theta component of force normal. Force normal sine theta equals mv squared on r. So that force is allowing us to stay in circular motion without friction at all. And then you can see, as I have here in the notes, we substitute in for force normal, mg cosine theta. The m's cancel out. We get g sine theta over cosine equals v squared on r. So we get g tan theta equals v squared over r. And if that equation looks familiar to you, it should. That was our conical pendulum equation, right? Let's go back one more. Conical pendulum equation. G tan theta equaled v squared on r in the conical pendulum. And if you look at the geometry of the conical pendulum, the tension force plays the same role as the force normal. So in a sense, that car on the embankment is a conical pendulum, and it is actually referred to as the mechanical analog. So since they both are governed by the same equation, in mechanics we say that they are mechanical analogs. So this pink equation that I have is what is called the design value, or sometimes the ideal value equation for how fast can the car go even on the iciest day. So even with no friction whatsoever between the tires and the road, this equation will govern the circular motion of that car. So again, the m's cancel out. That's nice because you don't have to post speed limits for trucks versus cars. And this speed v then is going to give us a benchmark to use when we compare it to the actual speed and the coefficient of friction between the tires and the road. So there's really only two versions of these types of problems that you're going to have to address. One is where the car is going faster than the design speed, so v actual is larger than v design, so the car is going too fast. And the other case, of course, is if the car is going too slow, the actual speed is less than the design speed. Well, let's look at the too slow case first. Well, if the car is going too slowly, it's going to want to slide down the incline. So that means friction is going to act up the incline to try to keep the car from sliding down the incline. And I hope you can see the geometry here. Let me erase some of this since we've kind of muddied up this picture a little bit. So the frictional force when the car is going too slowly is up the incline, right? To try to keep the car from going down the incline. And the angle theta here is the same angle as the incline, so we get a frictional force cosine theta and a frictional force sine theta. So now we have to redo our F equals ma equations and analysis. So if you look at what we have here, in the y direction, we have this frictional force sine theta upward. We still, of course, have the force normal cosine theta upward. So we have both of these forces upward and mg down. So that is where this equation comes from, right? So force normal cosine theta up, that's just from the road itself. The force of friction sine theta is also up. Gravity is down equals 0. And in the radial direction, notice now we have competing radial forces. We have force normal sine theta still radially inward, so that hasn't changed. So this force here is still radially inward, but now we have a radially outward mu force normal cosine theta equals mv squared on r for our circular motion. And these two equations we would use together with whatever numbers they give us for the problem to figure out what coefficient of friction we would need, or what speed we would have to increase to for a given coefficient to be able to make the circular motion and not have the car go up or down the embankment. Well, I'm going to leave it to you to go through the details of when the V actual is greater than V design, but if the actual speed is greater than the design speed, we have, and again, let me erase this, we now have the case where the frictional force is going to act parallel to the road and down the incline to keep the car from skidding up the incline and off the embankment. So now this frictional force, this brown frictional force that I have drawn in here that is acting parallel to the road and down the incline is going to have two components. It's going to have a force normal, cosine theta. So this is force normal cosine theta, helping the car to stay in circular motion because it's in the radial direction. We have a frictional force sine theta now, pushing straight down with mg. So now I'm going to add and subtract the forces just like we did in the too slow case to get the sum of the forces in the y direction equals 0 and the sum of the forces in the radial direction equals mv squared on r. And as I said, I'm going to leave it to you to make sure that you understand each of the terms in these equations, and if it does not seem to sit right with you, we can talk about it in class together. So this is the basic thought process and analysis that you're going to need to use when you look at cars on embankments, and hopefully this will help you solve these types of problems.